今天，当走进几乎世界上任何一个涉及低温强磁场下物性表征的高端科学实验室，你都有可能看到带有 Quantum Design 标识的研究设备。通过40年的不懈努力， Quantum Design 已经把低温强磁场下的物性表征从传统极端条件下复杂的搭建过程，转变为全自动的一键操作，极大提升了低温强磁场下的研究效率。Quantum Design 公司创立于1982年，总部设立于美国圣迭戈。40年间 ，Quantum Design 陆续在全球多个国家和地区设立子公司，服务于全球科研用户。在过去的40年时间里， Quantum Design 秉承 By Scientist for Scientist 的理念，由具备强大技术背景的科学家组成研发团队，不断探索前沿测量技术，推出各类新型测量功能，以满足多种多样的测量需求，精益求精，与时俱进。同时 ，Quantum Design 也一直积极投身于科研、教育、环保等领域，为全球科学家提供优质的技术支持与服务，并赢得了行业内的极大认可。现在 ，Quantum Design 正助力全球3000多家高端实验室的科研用户，在低温强磁场下展开科学探索。在中国设立超过了300万美元的样机实验室和专业的售后服务团队，为国内几百家一流的科研用户单位提供服务。在超导、磁学、半导体、电子、二维材料、化学等各个领域， PPMS 综合物性测量系统和 MPMS 精密磁学测量系统助力了无数个重大科学发现。仅在过去的5年，利用 Quantum Design 旗下的 PPMS、MPMS 系列产品发表在 Nature、Science 正刊的科研工作就有近100余篇。科技永不停步，创新未有穷期。让我们一起期待 Quantum Design 奏响下一篇创新乐章。
Hello guys, my name is Jianing Chen from the Institute of Physics, Chinese Academy of Science. I'm the host person of today's online talk. This time we are very privileged to have Professor Markus Raschke from the University of Colorado Boulder this time. Professor Markus Raschke is a joint appointed professor by the physics and the chemistry department of the university. He is a very distinguished researcher on the topic of experimental nonlinear and ultrafast nano-optics. For me, as when I was a postdoc entering near-field optics research, I developed my career while reading many of Professor Raschke's well-known papers. And today, Professor Raschke will deliver a talk on ultrafast nano-imaging resolving structure, coupling, and the dynamics of matter on its natural length and time scale. Now I give the time to our speaker now. Yes, please, Markus. You can share the talk.
All right. Good morning, everyone, or good evening, good afternoon, wherever you're listening from. Okay, very good. Okay, should I start? Are we good to go?
Yes, please. Yes,
all
please.
Right, very good. I hope everybody can hear me well. So it's a great pleasure to this opportunity from the SPEC to present and for this webinar in China. It's a great opportunity really to reconnect. There's a lot of also friends and colleagues who I know have joined, and unfortunately, as many of you know, I've been visiting fairly regularly for a number of collaborations, and I hope we can resume this international exchange again soon and see each other also at conferences. So basically, while we're still in waiting for easier travel, then we take this opportunity to share some of our recent work. And what I like to discuss is actually what has been, or where we have made really great progress in our group and as well as other groups. And this is really bringing ultrafast spectroscopy to the nanoscale in a very systematic way. So what I will show you is how we are able to really do pump probe ultrafast imaging with far from equilibrium excitation, and I will say what that means, where we probe over a very broad time range, all the way from hundreds of picoseconds of thermal transport and phononic processes, then to faster time scales of electron-phonon interaction, and then nuclear wave function interactions and nuclear dynamics in molecular systems, and then all the way in the fastest time scales of especially electronic excitations and electronic coherences, really down to the few femtosecond regime. And this has been really a development which was a result of a very joint interaction, really both of very gifted graduate students and postdocs, and a number of external collaborators bringing in expertise, combined really with laser source development, which we have done with different companies. And what I should highlight really that most recently on this topic, we have started to collaborate with NeoSpec, which provides actually the unique platform for many of these experiments, especially this open platform for scanning probe, optical scanning probe microscopy by NeoSpec, gives you the opportunity then for accessing this tip sample near field regime with a wide number of different laser sources in a very flexible way. And this was then also essential also as we go forward in developing more modalities. So the work I'll present has been that of notably actually two group members who recently advanced in their career. Sam Johnson, he joined Intel, was graduate student, and Jun Nishida, who was postdoc with us from Stanford, and he has now started his own independent faculty career in Japan, also actually continuing the development of ultrafast spectroscopy on the nanoscale. And two current postdocs and new graduate students are working on the project. Wenjin Luo, especially, with an effort on the ultrafast coherent dynamics, and Roland Wilken, who joined us from Munich, who is working on ultrafast pump probe in quantum materials and molecular systems. And I would like to shout out also for our collaboration with Tao Jiang, who was former postdoc in the group, who's at Tongji University, and I'll have some of the results of his work on this very fast coherent dynamics at the very end. So really the key point is that we like to image the elementary excitations in matter, and they are defined on both ultrafast lengths and timescales, with a number of phenomena which are associated with the electronic and then with the lattice or atomic degrees of freedom. Correspondingly, then the electronic interactions are faster because of the light mass of the electron, generally in the few femtosecond regime. And correspondingly, within this time scale, the length scale of these interactions is then intrinsically in the nanoscale. And then as you go then to slower electronic processes and then to atomic motion, because of the higher mass of the atoms, this is then on correspondingly slower time scales in the picosecond range. And then phononic processes can then be also probing and sensing and interacting on longer length scales. And so the way to access this regime in a very universal way is through near-field scanning probe microscopy. As an all-optical technique, it allows you then with a variety of pulsed laser sources to drive the system out of equilibrium into a perturbed state, where then with subsequent laser pulses, then through a nonlinear interaction, again, optical nonlinear interaction in the near field, then you can do local probe spectroscopy of this induced dynamics and then the relaxation of the system back into equilibrium. And as it is established in ultrafast spectroscopy, from this then time resolved or time resolving, the time resolved probing of this perturbation, you can then separate the electronic and lattice and also the spin degrees of freedom. And this gives you then the unique insight into the elementary processes, which underlie a lot of the material function. And this is what I will tell you more about later. So really, optical near field, just to have a little background for those who are new to this field, allows you really to do super resolution imaging. And in this scattering scanning modality, then really with any optical modality, and therefore also ultra-fast, nonlinear, and coherent interactions. And what we do is really we do dynamic imaging, and this then allows you then not only to probe and understand the material, but then really also a form of enhanced and controlled way of manipulating this light-matter interaction. And so the ultra-fast nano-imaging has been really a focus of the group for actually since the beginning, and it has been a long way to really achieve a number of these goals, in particular that how we can implement far from equilibrium excitations to really probe the material and probe the excited state dynamics. So not only ground state spectroscopy, which is what you do in all other forms of spectroscopy when you are coming with weakly perturbing laser pulses, and sort of two main classes of interest for us and also for the wider community is really the study of 2D materials, where we are interested in excitons and Moiré physics, and then in molecular materials, where we want to probe polarons and vibronic coupling, and of course also electronic processes. What we also, and a lot of this is in some way related to population dynamics of these interactions. And what complements this is then on the faster time scale, how to probe coherent dynamics, where we do nonlinear interactions, and then really can image the nanometer femtosecond scale coherence in matter. And this is giving you very fundamental understanding on sort of a wave function scale, actually, of elementary processes. A key point is also in all forms of spectroscopy or nanospectroscopy is really looking at the coupled quantum dynamics. I will not have much time to speak about this topic. This would be for a separate talk, where we are now able to also probe really the delocalization, so non-local and vibrational wave function interaction between molecules. Intermolecular interaction is really a very fundamental process which underlies a lot of molecular functions, both from biophysics to many photonic molecular materials and optoelectronic properties of molecular materials. And we are now really able to probe on the wave function scale this intermolecular interaction, which really then gives rise to the properties of molecular materials. But what I'll do is at the very end, I'll touch briefly into a whole different regime of light matter interaction. And this is when the light state really hybridizes with the quantum state of a material. This is what's called then the strong coupling regime. And we can achieve this actually because the tip and the sample, if it's the metallized sample form, what could be termed actually as an optical cavity, which is a very small mode volume. This is where this terminology picocavity then arises. And this is where we are actually able, even on the level of single quantum emitter, at the single photon level, then do cavity QED type physics. And this is what is relevant for a lot of quantum information applications, but also addressing then again fundamental processes of what limits actually coherence in solid state system, which is an informing question on many problems actually in solid state quantum information science. So let me then get back to the two classes of materials and describe to you briefly the science challenge associated with these, why we want to do nano spectroscopy, and then I'll show you how we advanced actually over the years optical scanning probe microscopy, then to achieve this goal of really probing what is highlighted really as how the structure and then leads through associated coupling of different excitation degrees of freedom, which we probe through the dynamic interaction to the material function. And so in 2D quantum materials, many of you are familiar that there is both a challenge, but also actually a science opportunity through the heterogeneity in these materials, sometimes in a non-desirable way through grain boundaries and defects, but also in a desirable way where in twisted bilayer heterostructures, actually new interacting quantum degrees of freedom arise, which gives rise to new quantum phenomena. And especially correlated electronic properties, including superconductivity. And that is an intrinsic nanoscale phenomena, which one likes to understand and requires probing on the nanoscale. But likewise, in many functional molecular materials, and here's a list of those. This could be perovskite photovoltaics, could be organic semiconductors, OLEDs, then a lot of biomolecular and other systems, where really the key point is that one wants to image electronic and photonic properties, and then really how they link to the elementary intermolecular level interactions where these functions occur. And so this brings then the question from a practical perspective, how can one image the quantum dynamics of these coupled degrees of freedom in quantum materials on these characteristic both lengths, time, and energy scales? And then similarly in molecular systems, where there comes in the additional challenge how to do this really non-invasively, especially because a lot of these functional properties, photonic and electronic or biomolecular, arise really from low energy molecular interactions. So this is a low energy milli-electron volt regime where much of these both desirable functional properties emerge, but also the energy scale at which defects and disorder really, for example, interfere with transport. And so there are sort of here little vignettes of then how we address this both in quantum materials and then in molecular materials. And I'll give some examples of this. And so really what we like to do is we like to turn essentially an ultrafast movie of we're following a exciting laser pulse of any of these electronic or lattice degrees of freedom. Then we follow the temporal evolution of these excitations and then trying to learn about the material. So I should say a few words about the energy scale. I already indicated that much of this is in this low energy scale of the mid-infrared to terahertz spectral range. And you can view it really that this is where this low energy landscape in these materials really defines these quantum or molecular material properties. And so in this low energy regime, in quantum materials, this is the regime of phonons and corresponding polaritons, magnetic excitations, also the pseudogap phases in superconductors and others. And at the same energy scale in molecular materials, you have the characteristic vibrational molecular responses, which give you also then chemically specific information. But then also, this is the energy scale of these intermolecular interaction, which we like to probe. So the way we have achieved this was really through a many-year painstaking process, both in, of course, also advancing nanospectroscopy, then also with continuous wave laser sources and other broadband light sources, So we spent a considerable amount of time also with the industry partner then to advance light sources and develop new instrumentation. This included also the implementation of synchrotron radiation used for IR nanospectroscopy, and then also the dissemination and implementation of infrared nanoimaging at different user facilities worldwide, at different synchrotrons, and then in parallel, of course, the tabletop light source development with different partners. But then also, and this has been pursued also by many other groups, was how we then can really do sort of a dynamic and multi-parameter imaging, that we don't only want to look at one optical channel or one scanning probe channel, and with the scanning probe tip in an atomic force or scanning tunneling microscope, interacting with the sample while you drive selectively this near-field interaction with the tip, which really acts as an optical antenna. Then there are multiple signal channels, which can also relate to the force of the tip sample interaction, inducing strain in a desirable way, and then resolving then several of the optical signatures. Could be spectroscopic line width, could be a peak position. And then from these combination of these efforts, as well as implementing then compressive sensing and other advanced computational imaging techniques, over the years, we've been able to really bring new modalities and new forms of optical signatures. This technique allows really then, which provides new material insight. And a couple of examples I will actually speak about a little bit: the molecular crystallography, the optical crystallography, where we actually use how the tip breaks the symmetry in the out-of-plane sample direction, which then allows you actually, through polarization control of the incident infrared light, to determine molecular orientation. We then did, in a number of works, really multimodal imaging, where we combined optical scanning probe also with electron and X-ray microscopy. Then a few years later, we were able to do more dynamic imaging, really time resolved. And this is where I'll show you sort of a highlight. Today, we did bring IR SNOM into the in situ and in liquid environment a few years ago. What I will also emphasize today is really how we image perovskite polarons, the electron-phonon interaction. This is the far from equilibrium pump probe experiments with excited state dynamic imaging. This really was achieved then just recently the first time. And I already mentioned the vibrational wave function spectroscopy, which I will not have time to speak about today. So just to highlight again, many of these developments, this was also then in part recently starting with NeoSpec, where we're taking a lot of prototype development and then develop them also for broader dissemination this industry, or conversely, we use platforms developed by NeoSpec for the ultrafast pump probe imaging. And then also NeoSpec has provided worldwide a number of instrumentation for synchrotron infrared spectroscopy, which is implemented at different user facilities, for example, in Berkeley. And so that is now also then for the non-expert users. You apply for beam times through a user proposal, and then you have free access to this facility and can implement your science program. And this has been actually tremendously successful over the last few years. So again, I will focus in this talk about how we really combine the feature of scanning probe microscopy, giving nanoscale structural information, and then in combination with short pulsed laser excitation, where we typically perturb the system in the visible spectral range, driving an electronic excitation, and probe the resulting electronic and lattice relaxation then in this infrared to terahertz spectral range. There has been complementary work, of course, of trying to access similar science questions then also with electron and X-ray spectroscopy. And this has been actually a field which has advanced very rapidly, and in many ways was sort of ahead of how we did this in ultrafast scanning probe microscopy. Because you have, when you do X-ray or electron spectroscopy, you have intrinsically very high down to atomic scale spatial resolution, but you're relying either on high energy photons as you do in X-rays or XUV spectroscopy, or in terms of the electrons, and this is often more perturbing, especially when we look at these low energy excitation of interest defining material spectroscopy. So ultrafast optical nano-imaging, as it was then in parallel by different groups, others and ours pursued, was initially focused on sort of carrier population dynamics and more weak excitations. There has often been just the focus on the time resolution, but not simultaneous spectral resolution. And so what I'll actually show, especially in ultrafast pump probe nano-imaging, where we provide really now a more universal way, a more generalizable way of how we can actually probe excited state dynamics to then simultaneous spectral resolution in addition to time resolution, how we can really do quantum state resolved nano-imaging, can do this with nonlinear and coherent interactions and a number of other really advances, which really provides this now as a way to really, as I would say, push really quantum dynamic imaging, right, into these to the fundamental limit and into a wide range of materials problems. And so what I will talk about is I will show you results now on how we do polaron and electron phonon coupled interaction spectroscopy. This is where we turn an ultrafast movie of the perovskite polaron dynamics. This is an elementary question about the performance of perovskites, not only actually in photovoltaics, but also more generally actually in laser and other optoelectronic applications for polarons. And then I show you results of nonlinear nano-imaging, really pushing into the fastest time scale, looking at the few femtosecond coherence, which I will show you in 2D materials. We started this in graphene and recently in transition metal dichalcogenites. And then I'll give you a very short perspective, actually, of the picocavity light matter hybrid states we form, which is a whole new level of quantum state spectroscopy enabled in scanning probe microscopy. So if you want to do ultrafast spectroscopy, as you know, you need a pump pulse which perturbs the system, and then a time-delayed probe pulse will then monitor the time evolution of the relaxation of the system back into its equilibrium ground state. And so if you want to implement this in pump probe spectroscopy, there is a wide number of challenges, technical, which I will not speak about in great detail. But you can imagine that it is different from far field spectroscopy, where it's much easier to not only separate these signal channels, but also where we want to selectively isolate actually then this probe signal, really selectively probing this excited state dynamic. So you have the pump pulse bringing the system from the ground to the excited state. And of course, your signal is generally dominated by the ground state probe response, and we want to selectively isolate now the pump probe signal from the excited state. And so to do this, you need to combine a number of modulations, both of modulating the light matter interactions through modulating the near field interaction, but also modulating the pump and probe pulses appropriately, so that you can selectively isolate the signal, and do this also in a spectrally resolved way, so that you really get then the full optical response function of this probe pulse signature from the excited state. And to do this, we take the pump pulse, which is directed onto the tip in proximity to the sample, and this is modulated. We then have the probe pulse, which is equally directed onto the sample. There is a delay stage, and then the probe signal is actually detected in the collinear backscatter direction. And then with the help of this interferometer, then we have another time-delayed reference field. And this is then brought to interference with the signal field, and this is called the local oscillator. And this allows you then to heterodyne amplify the signal field, and then also through this interference between the signal and the local oscillator, measure interferogram of this excited state dynamics, and then get the spectral information by Fourier transforming the signal. And then these different, so the tip sample distance is modulated, pump probe delay is varied, pump pulse is modulated in this reference field. And if you have a brilliant enough grad student and postdoc who can still keep the overview as these signals are fed into the detector electronics, then you can actually separate the desired signal. So what I made sound here in a few seconds like a very straightforward process was a long learning and development effort, and we recently succeeded then to implement that, and it's adopted also by other groups, and this is of course always the great joy, showing the success of the work. So let me tell you now in the first part really on what we have been learning about metal halide perovskites. As you may know, that halide perovskites are one of these very promising new solar energy materials, and we are currently achieving solar cell efficiencies which are actually successful and competitive now with actually even silicon photovoltaics, so they're approaching silicon performance. And it turns out that there is a very high level of defect tolerance, and this is different from other molecular and organic photovoltaic materials, and has been actually a big puzzle. Of course, with the big benefit that these materials are comparably easy to manufacture. And it was thought that this defect tolerance is actually a result of that following the photo excitation, the photocarrier excitation, that there is a dynamic lattice reconfiguration which stabilizes this photocarrier. And so instead of forming excitons, it is assumed that we are actually forming polarons, so that the electron and holes are isolated from each other and screened from this local lattice deformation. And so this polaron physics in perovskites is very poorly understood. And also it comes with an additional challenge that, in fact, this underlying soft lattice, which allows the polaron formation, also causes challenges, especially that this very dynamic instability of the lattice then also leads to a lot of structural heterogeneities. And this is from the atomic scale all the way to device scale, including compositional phase separations and other effects, which again would diminish the performance of these solar cells. And this is something which one wants to understand and see whether how to optimize this polaron stabilization and promote carrier transport without detrimental effects from phase separations or other non-desirable heterogeneities. So it tells you immediately that we have an effect or a science question here, probing the dynamics of these polarons with nanoscale spatial resolution to understand, especially in these polycrystalline structures, what are the rate limiting steps in the photophysical performance of these systems. And so we are actually picking then for these studies a triple cation perovskite for no other particular reason than this is one which showed in photovoltaic applications good performance, good photo stability, and it is composed of two types of cations. It's a cesium cation and then a mixture here of two organics, the methyl ammonium and formamidinium cation, and corresponding anions, and then the lead. And so questions are really, how does one engineer the composition for high stability and performance, and then really understand this polaron formation in these systems. And so we first perform ground state spectroscopy to study the heterogeneity and getting a first insight into any mechanistic questions about what underlies the performance. And so what we do here is we are probing now through a vibrational response, especially of this formamidinium cation. And we use this formamidinium cation as a local probe of these lattice deformations. This is a technique which we also developed, that we are using vibrational spectroscopy not just as a chemical marker. And so you see here this characteristic vibrational resonance in the near field of this formamidinium cation. But by actually doing precision spectroscopy, this is actually with a very high stable optical parametric amplifier, oscillator, and difference frequency generation mid-IR source, where we can really probe this vibrational free induction decay of this vibrational excitation, really as a sensitive local probe of this local structural environment by precision analysis of vibrational peak position in line width. And so from this multi-parameter analysis, we can get information about the coupling of this formamidinium cation to the structure, and therefore get information on the structural distortion as a result of heterogeneity on the nanoscale in the cation and anion distribution. We get insight into vibrational dynamics, so the lifetime of the vibration is associated to the strength of this lattice coupling, and then the intensity of this spectral phase signal in the near field gives you information about the composition of heterogeneity. So here's an example how these measurements are performed. We do atomic force microscopy overview imaging. Then we'll zoom in into a smaller scale of these different granules from this polycrystalline structure of these films. And then we analyze line widths and peak position, and then correlate with some of these topographic features and these grains. And then we'll, of course, study intragrain and intergrain heterogeneity. And then we can modify the film, for example, in water vapor annealing. Then you actually see, as a result of this highly flexible structure and a lot of diffusive processes, that these polycrystalline grains grow. And so we get sort of a ripening process, and then we can continue to monitor how this affects then the lattice. And so what we'll see primarily in a nutshell here, the result is that we actually see a correlation between a spectral narrowing and a blue shift, or inverse, we see a red shift in spectral broadening of this vibrational resonance. And these types of correlation then tells you actually a little bit what the microscopic process is. And this is that when you have, for example, a heterogeneous cesium ion distribution that gives rise to a distortion of this lattice, which then gives actually rise to stronger cation lattice coupling and faster vibrational relaxation. Whereas if the lattice is less perturbed, and instead of the cesium cation, you just have the organic cation, then we have a weaker cation lattice coupling and the slower vibrational damping. Now, we see the corresponding spatial heterogeneity, and this is also consistent with other work which has studied this process and problem by different techniques. But this is now the first time really that we see these, that there are spatially significant varying degrees on different length scales of this heterogeneity and how it manifests itself on a very elementary level. Of course, what we do not know at this point is how this affects then really the photophysical response in the solar cell performance. And so this is why, as a next step, then what we want to do is we want to really take this study to the ultrafast timescale, where we now want to probe this hypothesized polaron directly. And so the polaron forms as a result of the photoexcitation, where then this relaxing lattice then forms a bound potential state. And this was recently discovered that there is now a resonant mid-infrared interaction assigned to this polaron. And then this photoexcited polaron, and this is why the excited state dynamics is so important at this point, that only when you pump and excite and form this polaron, then we get a different level of interaction with these molecular cations and the molecular vibrations, which would then lead to a splitting with a spectral shift of the polaron, which is difficult to probe, but the excited state vibration and that spectral shift is expected to be a blue shift. And so if you probe the excited state vibration, we should see as a result of this polaron lattice interaction then a blue shift. And so this was for us actually then a good test bed actually for when we provide when we see how distinct the excited state vibrational responses. And so this is now in the first work where we established the basic principle of how we do visible pump IR probe nanospectroscopy. So we have the pump pulse forming the polaron, the probe pulse would then interrogate and measure polaron dynamics and the vibrational response. So if you do it now spectrally resolve in this transient vibrational response following the pump excitation, the Fourier transform of this gives you again this formamidinium cation response. And then if you compare that peak position with the ground state response, which we did the spectroscopy, which I showed you just earlier, then we actually see that we see a blue shift. And so this blue shift is expected and is consistent with this physical picture that this polaron cation coupling gives rise to that, to the spectral blue shift as a signature now of this excited state vibration. But also then when we probe at different positions on the sample, we see a varying degree of this blue shift. And so we can hypothesize about this heterogeneity, again, associated with differences in local chemical and structural characteristics of the sample. So then this, of course, prompts the question, then, can we monitor now this polaron dynamics in real time? And this evolution of these polarons, and so now if we would do probe and really do a full evolution of this spatiospectral and temporal dynamics, then we could learn something about the polarons. And so what you see here now is probing in the mid-infrared the pump-induced response as a function of time delay. Then there's a number of phenomena we can extract if you do now point analysis of different time slices of different spatial locations as a function of time. Then we can probe the decay and again the spatial heterogeneity of the decay of this polaron dynamics. Alternative interpretation is also that to think of this as a Drude relaxation. There is actually still considerable uncertainty actually in the question whether these are really polaronic or whether this is a more Drude-like carrier relaxation or combination. But then you see actually that there is a non-trivial sort of bi-exponential decay dynamics, and this is in fact a result of a fairly high density of polaron excited, which then relax through polaron-polaron scattering. So there is a excitation carrier density dependence, which can be analyzed. And the other thing is that we can look at the spectral evolution of the mid-infrared signature. And so what you see there is actually that at early times, and despite this high broad bandwidth of the of this mid-IR, the way we generate this as actually an optical parametric amplifier, non-collinear one developed for mid-IR generation, which provides this very high probe bandwidth with femtosecond time resolution, that we interpret this spectral feature as then the polaron Lorentzian response, and then be seeing that these tails of these of this Lorentzian fit, they narrow over time, and so this polaron response spectrally narrows, and this can be interpreted, in fact, through the model of large polaron absorption, which is a description of the expected response in this polaron potential. And so there are two key parameters as these polarons annihilate each other, and that means that the remaining fewer polarons can polarize a larger local lattice environment. So one can think of that there are more phonons increasingly available than for fewer polarons. These polarons grow, and as they do so, then they increasingly become more stable. And this is actually captured in this model, which has two free parameters. One is actually this polaron radius over the size over which the electron polarizes a lattice, and the other is this polaron stabilization energy, so the depth of this potential. And then from fitting this model to these data, we can extract this evolution of this polaron stabilization energy correlating with this polaron radius. And so these polarons grow over time. This is something which has been hypothesized previously, actually, from ultrafast diffuse X-ray scattering, where people have observed or signatures which suggest that more and more neighboring lattice sites get locally distorted as a result of this electronic excitation. And so with this model now, we can turn our full spatio-temporal data set now into a real movie, which we then fit these data and can convert and extract in time slices of polaron stabilization energy and radius. And so if you look at, for example, a time slice here at some particular time, then you actually see that there are locally regions where polarons are more stable and larger. And so this would actually be a desirable effect, because then you expect that also these polarons are have more time or less susceptible to defect scattering and can give rise to photocurrent, whereas there are locally regions which are less stable with smaller polarons, and this may be a less desirable thing. So what you're really looking at is in some way this really elementary process which underlies the whole photophysical elementary excitations in a perovskite solar cell, or at these higher carrier densities, which we are exciting here, then this would be more applicable than to lasing or other optoelectronic applications for perovskites. And what we see is that there is this non-uniformity in this photophysical response, and this actually tells you, and is at least the most significant result, that in this empirical processes by which the material chemistry is optimized, that we are certainly nowhere near a physical limit of the optical and optoelectronic performance of perovskite, that there is a lot of room for improvement if one could now optimize a cell where whatever the local chemical composition is of these structures is something where the entire system could be fabricated on. So with this, I'd like to summarize this part of where I showed you how, by far from equilibrium in excited state dynamics, ultrafast nano-imaging, we were able to really unravel sort of some of these difficult to handle or difficult to optimize elementary processes in perovskites are at work. This is both probing the molecular vibration as a local sensor of this local chemical environment on really the lattice scale, and then the coupled polaron and polaron evolution and stabilization dynamics of these carriers as they evolve is really a qualitatively new way of really studying perovskite photovoltaic systems, and then with really nanoscale spatial information by really turning these ultrafast movies. And here's an example then of, as a function of time delay from the analysis of these data, how this how this Polaron radius evolves in time and in space. So with that, I then like to switch and tell you a little more about now going to faster dynamics. So the key point here was carrier population and lattice degrees. And so now I will go in the remaining time to talk about really ultra-fast femtosecond coherent dynamics. And I'll make this part, this is a bit shorter because it's also a different scanning probe modality. But I still want to highlight that much of what I spoke about is applicable also to a wide range of 2D quantum materials, both probing equally lattice and other structural and electronic dynamics. But I just want to give you sort of a little highlight now how we are getting towards also probing the absolute fastest degrees of freedom in these systems. And this is really this very fundamental process of electronic coherence. So we have done a number of work previously in continuous wave spectroscopy, nevertheless fairly elaborate, looking at photoluminescence in Raman with a range of different processes, also nonlinear interactions, inducing local strain, taking advantage of the antenna properties of the scanning probe tip to sort out different excitonic degrees of freedom. We were able actually for the first time to probe dark excitons in the near field, and then we can take advantage really of these picocavity effects of this very close coupling between the tip and the sample. But what I want to show you now is how we actually combine this with femtosecond pulse excitation to probe some of the elementary processes at the example of graphene. Graphene is a very exciting optical material, in fact, because of this Dirac cone band structure and these very strong resonant transition dipole transitions. You can then at any wavelengths and actually gate tunable by shifting the Fermi level can have very high nonlinearities, and you can have gate tunable nonlinearities. This is actually Jiang Tao's work at Fudan, and he was then leading this effort in our lab to bring then four-wave mixing spectroscopy to the nanoscale, probing graphene, ultra-fast four-wave mixing. So the way we do this was that we had implemented a tool with the goal of how can we make a few femtosecond light pulse on the nanoscale. And so here, in contrast to these experiments I showed you previously in the conventional way of where we illuminate the tip apex directly with the laser pulse, here we actually illuminate the shaft of the tip where we produce a grating. And what we take advantage of here is that the tip acts as a conical waveguide. And if you launch a propagating surface wave, a propagating surface plasmon on a metal structure, in a conical metal structure, one can show that the index of refraction actually diverges as this radius decreases. And consequently, then the group velocity of this laser pulse slows down, the wavelengths get shorter, and this leads to adiabatic compression of this laser field to the apex. And so you see no emission then as you have this evanescent surface plasma propagate, and only at the very apex, then when you hit this discontinuity in the propagation direction, then you actually form this compressed femtosecond pulse, which then you can use as a local light source for nano-imaging. So this would be a talk in itself. There's a lot of fascinating plasmonics involved in this process. But suffice to say here that what we do here is that we generate very short transient and also optimize the pulse shaper in this apex where we have this nano-compressed optical field. And then we can do four-wave mixing spectroscopy. So here's the fundamental light field of a few femtosecond pulse in this apex. We filter the short wavelengths part. Then we take advantage of the nonlinearity either on the tip itself or in the sample through wave mixing of this fundamental component to regenerate actually light at then the short wavelength. So basically we're rebuilding this pulse, and then this light is is detected. And so what we like to probe is now really the coherent electron dynamics and heterogeneity of coherent electron dynamics. So probing different spatial locations and then looking at the time evolution of these coherent excitations. And so here is how we establish this principle, where we do a very simple experiment. In practice, still difficult, but in the sample system, simple. It's a edge of a polycrystalline gold metal film, where within the bandwidths, we are exciting localized surface plasmons. And you see then the forward mixing signature of these. And then they interact and they decay. And this decay of this electronic coherence is determined by the true derelaxation time, which is very fast because of the high carrier density. And so within a few femtoseconds, really, we are seeing this decay of these plasmonic localized hotspots. And if we evaluate the data and we can then normalize by looking at the signal in this way, normalize to the strong emitter, then you actually see that there are differences in the time evolution of these different plasmonic structures, and then we can determine spatial heterogeneity in this ultrafast Drude carrier response on this few femtosecond timescale. So this is fundamentally informing on a lot of these elementary electronic excitations in the metal, and we want to then apply this, for example, to graphene. So now here you're seeing the temporally integrated four-wave mixing signal on sheets of graphene, monolayer, folded, bilayer, trilayer. And there is, in fact, and I don't have time to talk about this, there is in the nanoscale, there are different in nonlinear optical response actually differs. We're getting non-local effects of the nonlinear response. But what I want to show you is really just the time resolution. Then when we image here the edge of a graphene film as a function of time delay, then we'll see there is not only spatial heterogeneity in this decay, but we see extremely fast electronic decoherence in graphene. And this, to some extent, was initially surprising because people had hoped that there would be very long-lived coherence in graphene, simply inspired by many other of unique optical properties of graphene, especially the strong nonlinear response would indicate maybe there is very long coherence. But the carrier scattering in graphene is very weakly screened. And this is actually why you get exceptionally fast energy and momentum redistribution of these electrons through a number of processes, such as impact ionization or Auger recombination, which gives rise to this extremely fast coherence. Okay, so I'm seeing I'm actually running a little out of time, so I want to actually just really give as a last vignette a extension of now how we are having already this high level of control of the light-matter interaction with spectroscopy, that we can actually go another step further. And in all these processes so far, even though we are perturbing the system, we are still probing what we would describe as an intrinsic optical response of the material. So the material quantum states are not modified to the optical field. And this changes fundamentally in cavity optics, and also then in cavity nano-optics and nanophotonics, where then the light field really hybridizes with the quantum state of the material. And this is actually indeed possible with these exceedingly small mode volumes, this very tight confinement of the optical field to the apex of the tip. And if you achieve this, then there is, in weak coupling, you can observe Purcell enhancement, which is related to a modification of the mode volume. And then at sufficiently small mode volumes where the coupling and interaction rate of the photon field with the quantum state exceeds any loss rate, then you get into this strongly coupled and Rabi oscillation regime, where you have this coherent exchange between the light field and the quantum state of the material. And so this strong coupling and Rabi oscillation, this is the hallmark of is needed for many quantum information applications, and it's entangled states between light and matter. and is very important for quantum sensing and transduction, and also quantum computing applications. And because of generally large mode volumes of conventional cavities, that limits the strength of the light-matter interaction. So you have to turn off dissipation channels through cooling. And we could show that with these very small mode volumes, even at room temperature, we can actually achieve strong coupling. And we term this in tip-enhanced strong coupling, where this very small mode volume here between the tip and the metallized substrate with quantum dots, we can achieve strong coupling of the single emitter. And so we showed this a couple of years ago, and now we are extending this also in combination with molecular system and looking at coupling between the vibrational and electronic degrees of freedom then in strong coupling. And we can do this also just in the mid-infrared probing vibrational excitations. And so doing molecular per cell enhanced IR vibrations, we showed this also with a parallel effort where we then can really do per cell enhanced vibrational and vibrational strong coupling, which allows really for single molecule detection and forms of molecular optomechanics and quantum transduction. And so this whole field is an emergent field. There are increasing number of people working in it with a wide range of modalities of building different cavities and so forth. So it's an exciting area which we can implement also in tip-based and scanning probe spectroscopy. So with this highlight, I'd like to sort of go back and summarize and give you a little perspective of ultrafast nano-imaging. We can probe collective many-body excitation. We can probe coherent dynamics. We can extend this now to different forms of multimodal, but also multidimensional nanospectroscopy. And then with strong and shaped laser pulses in these picocavities, we could imagine a whole new world of nonlinear optics and forming hybrid light matter states. And with that, I think I'd like to thank you for your attention. There is opportunities here for grad students and postdocs working in the group in this broad interface of ultrafast nanospectroscopy, which we pursue really in conjunction with national user facilities, with also laser development, with companies, with NeoSpec on implementing new modalities to the nanoscale, and really addressing fundamental science questions at sort of the most elementary level of spatial, spectral, and temporal nanoimaging at the femtosecond and nanoscale. And with that, I'd like to thank everyone for their attention, and I'm happy to take questions.
Okay, thank you very much, Professor Raschke. Now we are waiting for the backstage to collect the questions. But I have a few questions actually I want to ask. The first one, in the beginning of your talk, you mentioned somewhere in the slide that the limit of this temporal resolution in near field is like 50 femtoseconds. And I would like to know that what limits this temporal resolution, and did you achieve this in what kind of condition?
Well, so generally the time resolution is essentially given by two effects. One is, and maybe I'll highlight this here. So a traditional perspective is that the time resolution is determined by the pulse duration of your laser pulses. And so if we have 10 femtosecond pulses, we can resolve generally 10 femtosecond time resolution. But in addition, and this has been a transition now in a lot of laser pulse development, that it's not just a question of pulse energy, but really low noise and precision, and also how we detect the optical signal. So one can actually even get time resolution which is somewhat faster even than the pulse duration itself. And so in this case, we are resolving down to 6 femtosecond dynamics nominally with even 10 femtosecond pulse duration. And so it really depends on how accurately you can determine phase and amplitude of the optical pulse. So here we're using very short pulses in the pump probe measurements. These are amplified laser pulses. and in this case, depending on the system of the amplifier and how the parametric generation then produce, in this case, on the order of 200 femtoseconds, then here the dynamics is limited to about 100 femtosecond time resolution. But also the key point here is it's not always a question of that you want to not always probe the fastest processes. So as these perovskite dynamics showed, here the dynamics is controlled really by this polaron dynamics, which is on the order of tens to hundreds of picoseconds. So it's not a race to achieve always the fastest time resolution. It has to be selective for whatever the dynamics is. And in fact, a lot of fundamental material science questions are actually more on sort of this long-lived dynamics. And so in here, you actually want long-lived polarons which control the photophysics. And this has been traditionally difficult, actually, in ultrafast pump probe to actually, it's sometimes easier to do to resolve fastest processes than to probe longer lived states. So the short answer is it's always dependent on your application, but there is not really a fundamental limit. It simply depends on your light source and how short a laser pulse you can engineer.
Okay, thank you. And the second question is regarding this polaron. Actually, in the near-field amplitude images, there's no actually clear pattern. Like, for example, processing in graphene or processing in other system, you see these fringes or you see some particular patterns. Actually, in this near-field amplitude images, we see it's like arbitrarily distributed hotspots. And my question is, from this kind of images, what is the justification that you can determine what you see is a polaron or something else?
Well, so the question whether it's a polaron or a Drude response is actually open. There's this spectral signature what people have observed has been attributed to polaron. There's theory which supports this, but there is a growing body of literature which is now thinking also whether this is simply more a Drude type or a combination response. So this is difficult to determine, but in terms of the heterogeneity, it's of course not that we have phonon polaritons, right? This is where you would get this pattern you describe, because then you have propagating phonon polaritons which edge and tip scatter. In this case, this dynamics is determined by the polycrystallinity. And if you look closer at the data, then you can actually see that on different crystallites, then there are different, slightly different dynamics. The correlation, and there would be a lot more data to show to what extent this temporal evolution in these localized spots is correlated with both on this sort of intra-grain, there's heterogeneity within the grain, there is heterogeneity between the grains. And so these are difficult to analyze data in that sense, because it's not a single crystalline system where you say can launch a phonon polariton or a plasmon polariton like in a 2D material, right? But it is nevertheless significant, because that is just the nature of these perovskite materials, right? And we are using this on purpose to show what you can learn actually in such a highly heterogeneous system, right?
Oh, thank you. Let's see if we have some more questions from the online audience. Is there any questions?
Did they write? Do we get the question in writing, or will they?
I think they're writing, but I cannot I'm waiting for the backstage operator to send these questions to me, but at the moment I don't see something.有问题吗 ？Okay, actually they say for the moment there's no question. Actually, I think you thank you very much. Thank you very much, Professor. I think you just provide a lot of information. Actually, the very latest information regarding this nano temperature and the super resolution of this nanoscopy. I think yeah.
Yeah, no, it's a great pleasure. And if anybody has follow-up questions, we can always answer offline. Maybe you can collect those, and we can answer those by email or something. Yeah.
Thank you very much. Thank you. So if it's okay, I think we can thank the professor again, and we can just close this online talk. Thank you very much.
Yeah, thank you.